Last video, we saw that groups are mathematical objects that describe symmetries. We saw our first group, D4, the group of symmetries of a square. The key idea is that if we mark the corners of a square with numbers, then apply a symmetry from this group, after removing the markings, the square looks exactly the same. This numbering also lets us see more concretely what the symmetry does. The symmetries of a square could also be called geometrically invariant transforms. Symmetries arise when we have invariants. So now let's see a new type of invariance, which leads us to a new symmetry. So what is this new symmetry? Let's think about things that we can mark, could be with numbers, letters, or even colour or shapes. Then transform, i.e. move, rearrange or shuffle, and somehow something stays the same. So if we removed the markings, we wouldn't be able to tell that anything had happened. Feel free to pause and think for a moment if you can think of something that might have these properties. In fact, this object uses all four types of markings, and we shuffle it. How about 52 blank rectangles of card, marked with various combinations of numbers, letters, colours and shapes, that we can shuffle to any ordering, otherwise known as a pack of cards. Perhaps we could say it is invariant up to ordering. See that when we've removed the markings, it's impossible to tell that we shuffled the cards. This makes sense. If we shuffle a pack of cards, we still have a pack of cards, just with a new ordering. The object stays the same, invariant to the order. It'd be rather unfortunate if not, and while shuffling we could accidentally alter, subtract, or even duplicate cards. So let's have a look at these shuffle groups. All the possible shuffles of 52 cards is probably too many to consider. So let's just look at 4 cards, and consider the group of shuffles of these 4 cards. As we saw before, a group is a set of symmetries, which is in this case all the possible shuffles. So we can list them out. Put them in a set, and construct our group. Again, as we saw with symmetries of a square, drawing out the symmetries visually is too much effort, so let's just list out the result of the shuffles in square brackets. This notation is now hopefully a bit easier to read. See that starting from any number of objects we could construct a similar shuffle group. We've chosen cards for this group, but any other distinct objects would also work fine. We call these shuffle groups Sn, the symmetric group of n objects. To construct Sn, we take n objects and make a group of all the possible shuffles, or permutations of these objects. So now you might ask, in general, how big is this group? And perhaps more importantly, why do we call it the symmetric group? If all groups are sets of symmetries, what makes these shuffle groups so special that they earn the name symmetric group? First we'll answer the easier of the two questions. How big is a symmetric group of n objects? Let's look at S4, the group of shuffles of 4 objects that we saw before, and see if we can generalize the result. What we want to know is the order of S4, i.e. how many elements are in the set. S4 is not too big, so we can just count them. We see that S4 has 24 elements. But why is this? One nice way to see this is to arrange the elements in a structured way. Here, I'll use a tree diagram. We can first group the shuffles by what the first card in the shuffle is. We can pick any of the 4 cards. Then each of those branches has 3 branches leading off from it, for the 3 possibilities for the second card in the shuffle. Then each of those has 2 branches for what the penultimate card is. In fact, now see that we can fill in the shuffles completely, because there's only one possibility for the last card in each shuffle. The tree has 4 branches, each with 3 branches, each with 2 branches. So we can multiply these numbers to see that there are 24 places we can end up in the tree, i.e. 24 possible shuffles. 4 times 3 times 2 is commonly known as 4 factorial. You'll often see a factor of 1 included when factorial is written out. And we can amend the tree diagram to look more like this calculation if we like. So there are 4 times 3 times 2 times 1 possibilities. The takeaway is that the size of the group of shuffles of 4 objects is 4 factorial. So can we generalize this result? Well, Sn is the group of shuffles of n objects. We could draw a similar tree diagram with n levels, leading to n factorial possible shuffles. So in general, the size of Sn is n factorial. We've now started to investigate these symmetric groups as a whole. What about the elements of the group? Does a shuffle have any properties we can characterize? How do they behave? And could we use alternate notation to exhibit them better? Again, we'll start off just focusing on the group of shuffles of 4 cards, and see if we can learn anything about the elements of this group. We'll look at just one shuffle, for example this one, that leaves the cards in the order 4 ace 3 2. The shuffle is the action we performed on the cards to rearrange them into this configuration. The shuffle acts on 4 objects, the 4 cards. Remember, the shuffle is the transformation, not the cards themselves. Perhaps we might ask what happens if we do the same transformation again. What happens if we redo the shuffle, without resetting the cards back to their original order? So far we have done the shuffle once. We can draw that action like this. Let's do the exact same action to this new layout of cards. To repeat it, we just apply the same arrows. Now 4 occupies the ace's original position, so it gets moved into position 2, and so on for each of the cards. We can do the shuffle again, a third time, using the exact same process. But now we see something interesting has happened. This shuffle has now reverted us back to the original ace 2 3 4 order of the cards. To see why this happens, we need to understand the shuffle transformation better. We want to see what the shuffle is doing. Right now, we see what it did. So let's change perspective. See that right now, our square bracket notation tells us what place each card now occupies, i.e. 4 now sits where the ace was. Instead of seeing what now occupies a card's place, let's see what happened to that card, i.e. what place it got sent to. We will treat the shuffle as a map. Maps are incredibly common in maths and tell us where to send things. So now ace goes to 2, 2 gets sent to 4, and so on. But this is much more to write than our old notation, which gave us the same information, but more concisely. Well, we could use a trick to shorten it, by overlapping some lines. See that chains of arrows now start and end with the same letter, so loop back around. But ace doesn't get sent to ace. So let's correct that. And also shorten our notation even further. Now, hopefully you can see why doing the shuffle 3 times looped back to the starting position. we have a 3-card loop in the shuffle. Ace goes to 2, goes to 4, goes back to ace. So after 3 shuffles, each card in the 3-card loop ended up back where it started. Meanwhile, the 1 loop sends 3 to itself each time, so 3 always remains in its starting position. We could write these loops in brackets to keep the notation concise and on one line. This looks a lot like that strange notation we saw at the end of last video, and that's because it is the same notation. We've just discovered cycle notation, which is a standard way of writing elements of the symmetric groups, and can be used for other groups too. We call loops cycles. So here we have a 3 cycle and a 1 cycle. This notation lets us easily view these cyclic properties of the elements, at the expense of being a bit harder to see what order the shuffle leaves the objects in. Don't worry if this motivation seems a bit abstract or the notation confusing. We'll go through a more involved example later. But first, we can hopefully decode what we saw at the end of last video. Have a look at D4, the group of symmetries of a square. Here the labels 1, 2, 3, 4 that we marked the corners with are used in the cycle notation. We can now see why the cycle notation looks like this. For example, the identity, the do-nothing symmetry, is just 4 1 cycles, as each corner is sent to itself. Or the diagonal reflections, which just swap 2 corners. These form 2 cycles. We don't usually write 1 cycles, as we did for the identity, so we can focus on the key properties of the group element only. See that a rotation 90 degrees forms a 4 cycle. Perhaps here the cycling intuition is strongest. Doing this rotation 4 times is the same as doing nothing at all. Feel free to pause and check that you're happy with the rest of the elements converted to cycle notation. So to recap, we've seen that shuffling is a symmetry of a set of objects, and found an alternative way to represent these shuffles: cycle notation. This helped illuminate why doing the same shuffle multiple times can lead to ending up back where we started. We've seen how the cycle notation for numbered corners can also be used to represent symmetries of a square. But can we write any shuffle in cycle notation? And do they all loop back round to the identity? Well, let's now see how we can convert any shuffle, or permutation, to cycle notation. Let's look at a further example using a full suit of 13 cards. Do a shuffle. And see how we can go about converting this shuffle to cycle notation. There is in fact a method to convert any shuffle to cycle notation, and we'll go through that step by step now. Let's add another row of cards below, in the starting order. As we methodically work through this shuffle, converting to cycle notation, we can use these to visualize our progress. We start by finding the cycle beginning with the ace. Ace goes to 4. So we write that in next. 4 goes to king. King goes to 5. And so on. We continue filling in this cycle. The cycle ends when the empty space left by the ace is filled, which we know must happen eventually, so we follow the cycle through until that happens. We see that 2 fills this space, so the cycle loop is complete. We denote that with the closed bracket. Now, begin the next cycle. We'll start with the lowest available card, i.e. the lowest card we haven't moved yet, which in this case is the 3, which goes to 10, goes to 9, goes to 6, goes back to 3. Now all the cards have been used, so we're done. This shuffle has been converted to cycle notation. In practice, we don't need the second row of cards. We can just trace through each cycle. In this example, we could have just used the blue highlights. We see that this shuffle is formed of 2 cycles, a loop 9 cards long and a loop 4 cards long. We call these a 9 cycle and a 4 cycle. Cycle notation lets us see what's going on under the hood of the shuffle. We see the underlying structure of this seemingly random arrangement of cards. We see that following this method, any shuffle can be written in cycle notation. Perhaps we might now suspect that all shuffles eventually loop back round to the identity too. So let's reset this shuffle and investigate what happens if we do it multiple times. Notice we can draw two loops and arrange the cards onto them in a way that aligns with the cycle notation we produced before. Now, we see the cycles much more visually. So doing the shuffle is just rotating these two card cogs. If we do the shuffle to the cards too, we see the lines from before match up. We now have the cards in the arrangement obtained after one iteration of this shuffle, both on the cards on the top row and the cogs, according to the lines we drew before. So let's repeat the shuffle. For example, if a card is in the aces position, it will be sent to the fourth position. 2 is in the aces position, so it will be sent to the fourth position. Doing this for all the cards is just doing another turn of the gears. It might help to think back to the example with 4 cards, which introduced cycle notation through this concept. So after 2 iterations, the final shuffle looks like this. Note that now we still have a 9 cycle, but also 2 2 cycles instead of the original shuffle's 4 cycle. The cycle structure need not stay the same. Our card cog diagram doesn't change though, because we are doing the original shuffle over and over. The cycle notation below just keeps track of what the current shuffle is, converted to cycle notation. This is all starting to get a bit complicated, so let's add a counter to keep track of how many times we have done the shuffle. See that if we do it 2 more times, then something interesting happens. The cards in the shuffle's 4 cycle return to their original positions. When arranged visually like this, hopefully we can see that this is what we expect, since we have now done the original shuffle 4 times, so the 4 cycle has looped through. Let's carry on. In fact, any multiple of 4 works. After 8 iterations, the 4 cycle cards again return to their original positions. See, the same thing happens after 9 shuffles, with the cards in the 9 cycle. But the shuffle still hasn't looped back to the identity, because we need all cards to return back to where they started. So let's keep going. See that on all multiples of 4 and multiples of 9, the cards in these respective cycles return to the identity positions. What we need is a number that is both a multiple of 4 and a multiple of 9. Then we will have all cards back where they started. Well, what about 4 multiplied by 9? 36. Now, all the cards are back where they started. So see that doing the original shuffle 36 times is exactly the same as doing nothing, i.e. doing the identity symmetry. So now we see why all shuffles must eventually loop back around to the identity. If we just multiply the lengths of all their cycles, we're guaranteed to get back to the start after that many iterations of the shuffle. So to sum up, we now know what information cycle notation tells us about a shuffle. We've seen a method to convert any shuffle to cycle notation. We see that since all shuffles are just composed of closed cycles, if we iterate them enough times, we return to the identity. For example, if we multiply the lengths of their composite cycles, this number of iterations will certainly have that effect. Hopefully you can now see why this notation exists, as it gives us a somewhat surprising new perspective on permutations, or shuffles, as we've been calling them. So why do we call these shuffle groups the symmetric groups? if all groups are sets of symmetries. What makes these shuffle groups so special? So special that they earn the name symmetric groups. In fact, it turns out all possible finite groups are descended from these groups, which is quite surprising, given that these symmetries rarely feel like shuffles. For example, D4, the group of symmetries of a square, can be embedded in S4, the group of shuffles of 4 objects. What do lines of symmetry and rotations have to do with playing cards? It might help if we used more conventional notation for S4. Instead of ace, most textbooks will just use the number 1, and use cycle notation as the default notation for these symmetric groups. Now if we recall, we can use cycle notation to represent the geometric symmetries of D4 by viewing them as permutations of the markings of the 4 corners of the square, i.e., elements of D4 are just shuffles of the 4 corners. So we see that D4 does embed in S4, since all the permutations in D4 must also be in S4, the set of all permutations of 4 objects. In fact, it holds that all finite groups, and thus all finite symmetries, can be encoded in cycle notation, and so live in some symmetric group. So we call these shuffle groups the symmetric groups, because they are the most general forms of symmetry, and encompass all other finite symmetries. D4 was a neat way of doing it, but in general, this embedding is always possible. Next up, we'll see another group you may own. We'll look at an interesting property of groups. Perhaps we may even get to use our newly discovered notation. And we'll set the stage for the final video in this primer, which will introduce the symmetry underpinning Galois theory.